In this series of videos, we take a step up and look at some of the more advanced concepts of programming. Now, before you embark on these, you should have first watched all the Introduction to Programming videos, which we covered under the Programming Basics, and also had some decent practical experience in programming over a period of time. As such, these videos probably shouldn't be used in an upfront theory way to learn the more advanced parts of programming. Instead, come back to them after having programmed for a while and use them to reflect and consolidate. In this video, we take a look at recursion and how it can be used and how it compares to an iterative approach to programming. A recursive subroutine is an advanced programming construct, often a function which can call itself. The act of the subroutine calling itself from within its own subroutine is recursion. A recursive subroutine or function must have three very essential characteristics. Firstly, it must contain what is known as a stopping condition, or a base case. When this condition is met, the routine stops calling itself and will start to unwind. Secondly, for any other input values other than the stopping condition, the routine must call itself. This is the act of recursion. Lastly, the stopping condition must be reached after a finite number of times. Otherwise, the recursive algorithm will never end and will ultimately result in an error known as a stack overflow. This might all sound a little confusing at this stage, so let's try to unpick some of this to get a better understanding. Pause this video for a moment and look up on the internet what a factorial number is. Unpause the video when you're ready to proceed. So hopefully you found out the factorial of a non-negative integer, n, is the product of all positive integers less than or equal to n. We represent this in mathematics as n exclamation mark. So 3 exclamation mark, the factorial of 3 is the result of 3 times 2 times 1, or 6. 5 factorial is 5 times 4 times 3 times 2 times 1, or 120. 7 factorial is 5040, and so on and so forth. Now, imagine you were asked to write a program to output a factorial of a number that was input from the keyboard. How would you go about this? In other words, if the user entered 4, the program would output the factorial of 4, or 24. If they entered 7, it would output the factorial of 7, or 5040. You'd most likely try and solve this problem using some form of iteration or looping. Okay, so here we have our function. It's called factorial iteration, and the user passes in 4 here. We set our local variables answer and counter to 1, and then we go around this nice simple for loop. Counter is going to go from 1 to 4, and answer is currently 1, and we make it equal to 1 times the counter, which is 1. So 1 times 1 is 1. We go around the loop again, counter is now 2, answer becomes equal to 1 times 2, that's 2, and 2 goes in here. Now it becomes equal to 2 times 3, and 6 goes in here. Now it becomes equal to 6 times 4, and this is performing the factorial of the number. Eventually we've gone around the loop 4 times, and it chucks the answer out. Now we can rewrite this function in a recursive method, so here it is again. First thing you notice, it's slightly less lines of code. This is exactly the same function as before, but now it's using recursion. So the user passes in 4, and we say if the number equals 0, which it doesn't, then we are going to return 4 times, and then here we recursively call the algorithm, but passing in one less number, 3. The rest of this function doesn't get executed. We've gone back in to a recursive version of this function passing in 3. It's not equal to 0. We call it again, we pass in 2, and we pass in 1. Eventually, we're going to pass in 0, and if n equals 0, we hit our terminating condition, we set factorial to 1, and now we start to unwind recursively. Each time, this is going to get passed back into here, perform the part of the equation, the result is going to be passed back in, and we're going to end up with exactly the same result as we did using iteration. Let's compare these functions side by side. Remember, they do exactly the same thing, so which one do you think is better or more efficient in terms of memory? Well, actually, in this circumstance, it's the version that's using the for loop. Recursion in this instance is not very efficient at all. Every time the recursive function called itself, the processor had to remember where it was in the program before it jumped to the new copy of the function. That's so it knew where to return to when it started to unwind. It also has to remember the values of all the variables because they're local to that copy of the function. The computer does this using a data structure called a stack, which we looked at back in SLR 14, and this is very wasteful on memory. If you have a recursive algorithm that calls itself too many times before reaching the terminating condition, you can run out of memory and crash, and this is known as stack overflow. Let's try to visualize that function a bit better for you so you can more easily see the potential dangers and understand what's going on with recursion. So here we have the function rewritten in VB. There is our terminating condition, and there's our recursive call. And here's where the main program is actually going to start on line 9. And we're simply going to write out to the screen the result of calling this function and passing it 4. So we want to end up with 24. Remember, a recursive algorithm is a function which calls itself and has a terminating condition. And over here on the right are our stacks in memory. This one's going to hold the contents of the variable number, and this one's is our call stack and is going to keep track of which line of code to return to as the algorithm recursively calls itself. Currently both stacks are empty. So the program starts at line 9, proceeds to line 10, and we have a call to our function fact and we pass it 4. So we jump to line 1. When we do that, 4 goes into the stack as the number, the content of the number variable, and 10 has been pushed onto the call stack because that's the line we're going to have to return to when this function exits. Number's not equal to 0, so we skip to here, and now we hit a recursive function call. You can see here we are calling the function fact again, this time passing in number minus 1. Well, number minus 1 is 3. We're in a new copy of the function. This one has been stored away, and once I'm done, we're going to have to return to line 5 because that's where we left. So line 5 is going to the stack, but we're in this new copy with 3 being passed in. Number's not equal to 0. We hit the else, and we're going to hit another recursive call. And this time, we're going to pass in number minus 1, so we're going to pass in 2. So 2 gets pushed to the stack, and again we push on another return call because we're going to have to return to this copy. We're getting deeper and deeper into this recursive call. Same thing, number's not equal to 0. We hit another recursive call. We're in sort of 3 levels deep now. Number minus 1's passed in, so 2 is going to become 1. We push that onto the stack and also onto the call stack. We push another 5 because we're going to have to return here. Don't forget our original program started off here, but we're in 1, 2, 3, 4 layers deep into our recursive function. Number is still not equal to 0. So we go here and we recall fact one more time, now passing in 0 and another return to 5. Now watch what happens carefully. We are now 1, 2, 3, 4, 5 levels deep into our recursive function, and this time number has equaled 0. So fact equals 1. We are now hitting the return clause of this first function, and it's going to return 1 and we're going to have to come back. Now, when we hit this return clause, we pop out from the call stack the return address, so we know to go to line 5, and this 1 ends up in this part of this equation. And because we've hit this, we're also popping out the last value on the number stack. So now we end up with number, which is 1, times 1, which came from the previous recursion, and fact therefore becomes 1. Because we've hit fact, we now return that back out here. We're starting to unwind. This return call here has popped 5 off the stack, taking us back to this line, and that pops the last number off here too. Now we've got 1 times 2 is 2. That's going to come in here. Now we've got 2 returned from our previous recursive call, and number is now 3. 2 times 3 is 6, so 6 is going to come here. We can replace this. So number is currently 4 times 6, that becomes 24. One last time we've hit this return clause, we now proceed to line 10, so we come back here and we write to the screen 24. Generally, recursion should be avoided, but there are some situations where it is either the only way or is the best way of solving the problem, e.g. tree traversal algorithms or performing a flood fill in a paint application. Some of these will be explored in the exercises which accompany these videos over at craiganddave.org.